There is a moon orbiting Saturn right now that, by every rule we thought we understood about the solar system, should be completely dead. It sits nearly 1.5 billion kilometers from the Sun, locked in permanent deep freeze, barely larger than the state of Arizona. Nothing should be happening there. No volcanism, no chemistry, no warmth, just ice, silence, and darkness stretching in every direction. And yet, from its south pole, colossal fountains of water are erupting into space. Not small jets, not modest seeps. Enormous cryovolcanic plumes hurling hundreds of kilograms of water vapor and ice particles into the void every single second, feeding a ring that wraps around an entire planet. When the Cassini spacecraft first imaged those geysers in 2005, scientists had to check the data twice. What they were seeing simply shouldn't be possible. Enceladus is Saturn's sixth largest moon, and for most of its known history, it was treated as an afterthought. A minor satellite in a system dominated by Titan and the planet's own spectacular rings. Nobody expected it to be interesting. Nobody expected it to become, arguably, the most compelling target in the entire search for extraterrestrial life. I'm going to take you through everything we know about this remarkable world, from the astronomers who first spotted it through handcrafted telescopes, to the cutting-edge reanalysis of decade-old data that is still producing jaw-dropping revelations today. Because the story of Enceladus is far from over. In fact, if anything, it's just getting started. Enceladus was discovered in 1789 by Sir William Herschel, but even with the most powerful telescope on Earth at the time, a great 40-foot reflector built with his sister Caroline and polished over 18 painstaking months, Enceladus appeared as nothing more than a faint, featureless dot. There was no reason to think it was anything special, and so it remained unremarkable for nearly 2 centuries, when the Voyager 1 and Voyager 2 probes made their respective flybys of the Saturn system in 1980 and 1981. They sent back something unexpected. Enceladus had regions of its surface that were almost completely smooth and crater-free. In planetary science, craters accumulate over time like scars. A surface without them is a surface that has been recently reshaped. Something was actively erasing the geological record. More intriguing still, Enceladus sat squarely within the densest region of Saturn's vast E-ring. That wasn't coincidence. The ring is made of tiny water ice particles, and scientists immediately began wondering whether Enceladus itself was the source, whether somehow this tiny frozen world was actively feeding material into the ring system of a gas giant. These mysteries were taken seriously. Seriously enough that when NASA and ESA began planning what would become the Cassini-Huygens mission, Enceladus was written into the scientific objectives as a priority target. The spacecraft launched in 1997, looped around Venus twice to build momentum, and finally reached Saturn in late 2004. 7 years of travel for the chance to answer questions first posed by 2 probes that had spent only hours in the Saturn system. What Cassini found there would overturn decades of assumptions. In early 2005, during its very first close approaches to Enceladus, Cassini's cameras captured something that had never been seen before anywhere in the outer solar system: enormous active geysers erupting from the south polar region. Brilliant white plumes climbing hundreds of kilometers into space, powered by geological forces that had no business operating in a world this small and this far from the Sun. The eruptions were coming from a set of long, parallel fractures in the polar ice crust. Scientists would later call them tiger stripes, and for good reason. 4 roughly parallel gashes in the surface, each stretching nearly 130 kilometers in length, glowing with infrared heat and venting water ice, vapor, and gas continuously into space. The scale of it was staggering. These weren't occasional eruptions. This was a sustained, ongoing process, relentless and powerful. NASA made an almost immediate decision. Cassini would be redirected to fly directly through the plumes. This was not a small choice. It meant risking a billion-dollar spacecraft, flying it through an active geyser field at tens of thousands of kilometers per hour. But the potential reward was extraordinary. If those plumes were carrying material directly from whatever was happening beneath Enceladus's surface, flying through them would be the closest thing to directly sampling a subsurface ocean anywhere beyond Earth. The instruments on board registered the contents of those plumes, and what came back changed everything. Water vapor, yes, but also molecular hydrogen, carbon dioxide, and a range of organic molecules. The signal was unmistakable. Something chemically rich and energetically active was driving this system. The question was no longer whether Enceladus was geologically alive. The question was whether, in the ocean scientists now believed lay beneath all that ice, it might be biologically alive too. To search for life in any meaningful scientific sense, you need a framework. NASA uses a deceptively simple one. Life, as we understand it, requires 4 things: liquid water, a source of energy, the right chemistry, and enough time for complexity to develop. Walk through those requirements one by one on Enceladus, and what you find is simultaneously thrilling and humbling. Liquid water was the first box checked. Infrared mapping from Cassini confirmed tremendous heat beneath the south polar ice, and by carefully tracking the way the moon wobbled in its orbit over multiple years, scientists were able to show that a small, localized polar ocean couldn't account for the motion. The only explanation was a global ocean, a body of liquid water entirely encasing the moon's rocky silicate core, covered by an ice shell perhaps 20 to 30 kilometers thick. In 2025, a team from the University of Oxford and several partner institutions looked back at Cassini observations of Enceladus's North Pole and found something remarkable. Even there, in what should be the coldest and most dormant region of the moon, temperatures ran about 7 degrees warmer than models had predicted. The ocean wasn't a localized anomaly. It was everywhere, and it had apparently been there for a very long time. Energy came next, and this one required some creative thinking. Enceladus is tidally locked to Saturn, always presenting the same face to the planet. As it orbits, Saturn's immense gravity squeezes and flexes the moon like a stress ball, generating friction and heat deep within the interior. This process, called tidal heating, is the same mechanism that makes Jupiter's moon Io the most volcanically active body in the solar system. On Enceladus, models suggest the heat generated in the rocky core is transported upward as water percolates down through the porous silicate rock, gets heated, and rises back toward the ocean in focused thermal plumes along the seafloor. Hydrothermal vents, in other words, on the ocean floor of a distant moon. Chemistry is where things become extraordinary. Cassini carried a mass spectrometer capable of identifying molecules by measuring the mass of their ionized fragments. Flying through the plumes, it detected molecular hydrogen, a product of hot water reacting with rock at depth. It detected complex organic compounds containing carbon, oxygen, and nitrogen. And crucially, in 2022, researchers combing through the archived data found phosphorus compounds, completing the collection of every element considered essential to life as we know it: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. All 6 present in a moon 1.5 billion kilometers from the sun. Time is the remaining question, and this is where more recent analysis has been particularly reassuring. A study comparing thermal emissions across the moon's surface to theoretical models of internal heat generation found a remarkably close match between the two. The moon is producing heat efficiently, and that heat is being transported and radiated in a way that suggests this isn't a temporary episode. The ocean beneath Enceladus appears to be a stable, long-lived feature. Long-lived, in geological terms, means potentially billions of years. Enough time for life to not just begin, but evolve. When Cassini plunged into Saturn in September 2017, its destruction was deliberate. Scientists knew that a spacecraft contaminated with Earth microbes couldn't be left drifting in the Saturn system, where a stray gravitational nudge might eventually send it colliding with one of the moons it was protecting. And so the mission ended in a calculated death dive, and with it went our only platform for directly sampling the material coming out of Enceladus. But the data didn't end, and as analytical tools have improved dramatically in the years since, Scientists have returned again and again to the archive of everything Cassini sent back, finding things that simply couldn't be seen with the techniques available at the time. The challenge with analyzing plume material collected in a flyby is considerable. Cassini's instruments were smashing into particles at over 60,000 kilometers per hour. The way molecules fragment at that speed and energy is not the same as the way a chemist carefully breaks apart a sample in a controlled laboratory setting. A spectrum obtained from a high-velocity collision looks genuinely different from one obtained at rest, even if the underlying molecule is identical. Understanding and accounting for those differences requires years of dedicated research. A team at the Institute of Space Systems in Stuttgart spent over a decade doing exactly that work. Their results, published recently, drew on samples from Cassini's closest flybys, passes that brought the probe to within 20 kilometers of the Moon's surface. Particles collected at that proximity were minutes old, barely enough time for ultraviolet radiation from the sun to degrade their chemistry. They were as close to pristine ocean material as Cassini ever managed to collect. What those samples contained was striking. Not just simple organics, but complex multifunctional molecules, cyclic compounds, carbonyl groups, nitrogen-bearing structures, molecules that in a terrestrial chemistry laboratory would be recognized as precursors to amino acids and other biochemical building blocks. These aren't signatures of life itself, but they are signatures of rich, active organic chemistry in a water-based environment, driven by heat over a sustained period of time. That's about as close as a mass spectrometer can come to saying something interesting is happening here. The James Webb Space Telescope was designed to peer back to the earliest galaxies in the universe, to study the atmospheres of exoplanets trillions of kilometers away. Using it to look at a moon inside our own solar system is, in astronomical terms, almost unnecessary overkill. Webb can see Enceladus with extraordinary clarity. In 2023, a team led by Dr. Geronimo Villanueva pointed 10 hours of Webb observation time at the moon. What came back surprised even those who had spent careers studying Enceladus. The plume was massive, far larger than anything Cassini had directly imaged. Webb's infrared instruments traced the material ejected from Enceladus's south pole, spreading outward to a distance roughly 20 times the diameter of the moon itself, a sheet of water vapor and ice that dwarfs the world producing it, quietly feeding the Saturn system with billions of kilograms of water every year. But the observation resolved something that had puzzled planetary scientists for years. Saturn's upper atmosphere contains detectable quantities of water. This is unusual. The planet's own chemistry shouldn't produce it at the observed concentrations, and it had never been fully explained. Webb's images showed the answer clearly. Enceladus's plumes feed a vast donut-shaped reservoir of water ice, a torus encircling Saturn at the moon's orbital distance. As particles from this torus gradually drift inward, they eventually reach the planet itself. Enceladus, a moon half the size of Arizona, is actively adding water to the atmosphere of a gas giant 95 times the mass of Earth. It's a planetary influence far beyond anything its size should suggest is possible. Webb also confirmed that the plumes are not a temporary or sporadic phenomenon. The sheer volume of material being ejected points to a system that is robustly active, not flickering or winding down. For life, consistency matters enormously. An ocean that freezes over periodically is a much harder environment for biology than one maintained at a stable temperature over geological timescales. What Webb showed was consistency on a grand scale. Knowing all of this, it should come as no surprise that space agencies around the world are working to send something back to Enceladus. The difficulty is one of physics and funding. Saturn is far, and getting there takes years even with the most favorable launch windows and gravitational assist trajectories. Patience is unavoidable. The European Space Agency is developing a mission targeting a Saturn arrival around 2053, with an Enceladus flyby program that could include, in its most ambitious form, an attempt to place a lander on the moon's surface. If that happens, it will be the first direct contact with an ocean world beyond Earth. Separately, a project funded by the German Aerospace Center has proposed something almost science fictional in its ambition: a nuclear-powered ice mole a self-heating probe designed to melt its way downward through Enceladus's ice shell, extracting samples from untouched regions deep within the crust and eventually reaching the ocean below. The engineering challenges are formidable. The scientific potential is almost impossible to overstate. The JUICE mission, Jupiter Icy Moons Explorer, is already traveling through the inner solar system on its way to Jupiter, due to arrive in 2031. While Enceladus isn't its destination, JUICE will study 3 Jovian moons, Callisto, Ganymede, and Europa, all of which share Enceladus's key trait: liquid water oceans beneath ice shells. Whatever JUICE learns about those environments will inform how we approach Enceladus directly. And NASA's Europa Clipper, launched in 2024, is on its way to conduct close flybys of Jupiter's most famous ocean moon. The science we gather there could reshape our understanding of what icy ocean worlds are capable of sustaining. Here is what strikes me most about the story of Enceladus. When Voyager passed by in 1980, one of the most sophisticated spacecraft humanity had ever built swept through the Saturn system and photographed a plume of water erupting from the moon's south pole. The evidence was there, in the raw data, waiting. But nobody saw it until a retired amateur astronomer named Ted Strick sat down with archived images nearly 4 decades later and pointed it out. We found the evidence only after we knew what to look for. Science has a way of humbling the very people practicing it. For most of the 20th century, the assumption in astrobiology was that life requires proximity to a star, warmth delivered by radiation across the void. The habitable zone was a ring around each sun, a narrow band where liquid water could exist on a planetary surface. Everything beyond that ring was assumed to be sterile. Enceladus is nowhere near that ring, and yet here it is, maintaining a liquid ocean, cycling chemistry through hydrothermal vents, hurling the molecular building blocks of biology into space by the hundreds of kilograms per second. If life has found purchase in that environment, then the habitable zone as a concept needs to be dramatically expanded, not just around our own sun, but around every star in the galaxy. The physicist Jeremy England once offered a thought that I find genuinely difficult to shake. He suggested that given the right conditions, given energy flowing through a system of atoms over sufficient time, the emergence of self-replicating chemistry might not be a miracle. It might be an inevitability, a natural consequence of thermodynamics finding its most efficient paths. If he's right, then Enceladus isn't a long shot. It's another experiment running in parallel with Earth, quiet, cold, hidden under kilometers of ice at the edge of the solar system, but running nonetheless. We'll find out, perhaps in our lifetimes. And when a nuclear-powered probe melts through that ice and tastes what lies beneath, every question we've been asking since Cassini first spotted those tiger stripes will finally have somewhere to land. The universe, it seems, is not as empty as we once feared.